This is Lab 2, Motion of a Falling Object. So our purpose of this lab is to observe the motion of a falling object, collect observation data using Tracker, construct a computational model using code for gravitational and also gravitational with drag force, and compare the graphs of all three of those. Our system is a paper ball. Our surroundings are everything else like the air and floor. Fundamental principles are Newton's second law, gravitational force, drag force. So Newton's second law is force equals mass times acceleration. We can get our updated velocity formula from that. That's initial velocity plus acceleration, the change in time. And acceleration is the change in velocity divided by change in time. And our updated position formula is initial position plus the v average, which is initial velocity plus final velocity divided by 2. And we'll use these in our code. So gravitational force is the force of gravity equals negative mg j hat. M is mass. In this case, it is 0.0045 kilograms for a piece of paper. G is 9.8 meters per second squared. And j hat is just the direction of gravity. In the vertical position. So with these images down here, we can switch things around and understand how we get 9.8 newtons per kilogram as the acceleration due to gravity from the Earth in particular. Because mass 1 is going to be our mass of the object. Mass 2 will be, or m2, will be the mass of the Earth and the distance and gravitational constant right there. So drag force. Air is a mixture of particles, so they apply an upward force on the falling object, so we have to take that into account when we are talking about vertical movement. Drag force is defined by negative b, v squared, v hat. B is a proportionality constant, v squared is velocity squared, and v hat is the direction opposite to velocity. So when we add these two forces together, we get net force, so that gravity is pointed down, and drag is pointed up. Gravity is longer, so it has more force acting on the object. So net force would be pointing down, which is why the paper ball falls. So here's our intro. So this is what our observed and our two experimentals will end up looking like, and we'll discuss this later. This is what the tracker looks like in our video, and this is our code. Just some sneak peeks, I guess. So first, we observe the data using Tracker. So as you can see, the ball is falling, and then we get a bunch of these data sets right here, and we will be inserting these into the graph that we saw earlier, minus x values because we're not looking for horizontal motion, just vertical motion. Okay, so our code calculations for no drag force. So we start with the initial position, which is the same as the observed that we got before. Our delta t is just 0.1. Our grams is 9.8, which we found again using our little equations. And then j hat again is inserted that. B equals 0 because there's no drag force for this, so it's just keeping it constant. And then all of the f net vector. So because it's falling down, we're going to calculate a force that's being applied in the y direction. So, and again, that force is going to be gravity. So negative mg j hat. So we can plug in our numbers for there. And then we have to update our velocity, which we use this formula here. This comes from f net is a times m, and this is m, so it cancels out, so that's just a times delta t. So that's how I got that there. And then a position comes pretty much straight from there. Okay, so our experimental data using GoldStrip no drag force, we get this these graphs. So velocity change over time is very constant. We get these numbers, and these are the numbers. This is time versus position, which is this graph here, and we'll use these in our graph that I showed earlier. So then our code calculations for drag force, again, we start with initial positions. They're all the same. The ball is blah, 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 all these things. B constant does change this time, and we find that by plugging in numbers until our final position that we're given equals the final position of our observed. And I'll show that later as well. And then again, all of these get these updated position and velocity came from the same thing, but we do have to update our f net. So f net is the force of gravity plus the force of drag. So we have to add those together, and to get drag, we do b minus v squared times v hat. So that's what that equation is, and that's how we got that. So now we have experimental data using GoldStrip drag force. So again, we have velocity, change in time. This time it does have a change, and then position versus time looks like that. These are the numbers we'll be adding to our graph that I showed in the beginning. And then again, so this number right here at the end is the same or very close to the value of the last position that we had in our observed. So that's how we know we got our b value correct. And then, so these are all of ours together. So observed and drag experimental are extremely close. So we know that in our observed, there was, in fact, drag force being applied. Because our no drag experimental just, it's way off. It's not way off, but it's quite different and it's a little more consistent. So, but the reason why these aren't probably the exact same are probably due to center placement differences on Tracker. So whenever I was tracking it, it might be a little off, like this center of mass. Could be an inaccurate drag coefficient. I did just get it very close, but not necessarily the same. And then camera angle movement, like so, as we're taking the video, it could have moved, and then our position would be off, and all that sorts of things. And these are just a list of the data that I plugged in to put into here. So what does it mean? If we examine the velocity versus time prediction of our models with drag and without drag, can we find a terminal velocity? And so we can. So the model without drag has a linear negative slope, but the model with drag seems to level out at the bottom around negative 0.9 to negative 2 meters per second. This leveling out seems to indicate that terminal velocity as the force of drag begins to equal the force of gravity. This means that net force becomes closer to 0 because gravity points down and then drag force points up. So if it's leveling out, velocity is leveling out, then net is becoming a little bit closer to 0. So what if? Imagine if the object was initially thrown downwards. So how would this affect terminal velocity? Would it be the same, different, whatever? So it looks like the whenever it was thrown down, which to do this we just change the initial velocity to be 0, negative 1, 0, because that's instead of 0, the 0 vector, because it's being thrown down, so force is being negative, yeah, in the y direction. So this basically seems to level out at nearly the same place, like negative 1.9 to negative 2, if you look at the graph, but it does seem to do it a little bit steeper, so maybe it just gets there a little bit quicker, but for the most part, it is the same, like terminal velocity. So conclusions: in the observed system, there's drag force being applied on the ball. Vertical motion includes force of gravity and usually some upward directed force, in this case, drag from the air. And then force of gravity plus the force of drag equals the net force applied on an object in vertical motion when it's being dropped. Thank you.